How's it going, guys? Today I'm going to talk to you a little bit about the CAN questions that I got. Is it possible to make a CAN bus sniffer? The answer is yes, but I don't recommend it, especially if you're new to this. There's a lot of devices out there on the marketplace that are incredibly cheap and robust, but there is the ability, and I've made my own. I've done it, and it's time consuming. If you're just needing a device. There's already ones out there. If you're looking for it to do specific, very key technical things, it may be worth your time. But you're going to be digging some time into it, and it's not very fun. There's a lot of libraries and stuff like that for Arduino out there, and I do know they exist. I've played with plenty of them. But the reality is what you're typically trying to do is either already been done or isn't going to be referenced based on the library, and you're going to be doing a lot of coding. How arbitration works. Arbitration works basically with the least value having the highest priority, kind of like if it was like rank in the military. If a sergeant was trying to talk to a colonel and the colonel interrupted him, the sergeant would stop talking. And this goes with the arbitration ID and the message being portrayed. So you won't have a device try to interrupt once the message is already started and it's got past the arbitration phase. So if we both tried to start talking at the same time and I have more seniority or more rank than you, and you can tell that based on the arbitration ID, the message ID, the lower the message ID, the higher its priority. So if you have an ID of 100 and an ID of 200 and they both try to send a message at the same time, ID 100 will take precedence and ID 200 will back off and try again once he's done speaking. Wiring and terminations. Wiring and termination. This has been, it's pretty understood for the most part, but there is pretty much a standard. It's called ISO 11898-2, which is what most of the devices you'll ever work with are connected to. I'm not going to get into various key niche based that are run at lower bus speeds and more fault tolerant and things like that. Anything you run on, if we're dealing with motorsport stuff or automotive stuff, the bit rate's going to be at most likely, unless you're dealing with like interior CAN or something that's just not common, it's going to be 500K for most OEM applications on their Motorsports CAN. Very rarely will it be 1 megabit or 250K, but they do exist. Mercedes has an interior CAN of 83.333 bits per second or kilobits per second. It is out there, and you just got to be an understanding that most likely 500K is whatever information you're looking for is going to be at. In the motorsports world, a lot of things try to run at 1 megabit, but the three typical values are 1 megabit, 500K, and 250K. Haven't really seen anything jump past that. Just doesn't exist. You're going to have a terminating resistor or a device that has an embedded terminating resistor at the end of the nodes. Your bus length will be limited to a specific length, total length, based on a handful of factors. One of those factors is how many devices you have on the network, and the other one is at what bit rate or what bus speed you're sending information on. The lower the bit rate, the bus speed, the longer your bus length can be, because there's that time between a dominant and recessive bit, or each state of a bit. How to turn raw bytes into usable information. Raw bytes into usable information is probably one of the most complicated things for a lot of people to understand, because there's a lot of various ways manufacturers can go about it. They could use values that are really high, unsigned and offset, or they could use signed and no offset. Most of the times it's kind of like this, you have to pay attention to and see how it works and see what you're looking at and see what data is changing in order to understand that. I'm going to go over to Kvasir's DB editor to try to explain this a little bit as well, because a lot of people it's very difficult to understand how it typically works. Almost everything will transmit information at a bit level from least significant bit being on the right to more significant bits being to the left of it. And I make that statement when it's only in that specific byte. When you start talking about byte order, that can change. So information will go from the right side of the byte to the left side of the byte being least significant to more significant almost always. What will change is where does it overrun to the next byte at. So a good example, I'll type in 9 here. Okay. So you see we overrun to the bit to the left, or to the byte to the left of this third byte. So it's going into byte 2. So if we were looking at this value, it would kind of look like if you had 2 calculators together and each calculator only had 8 positions on it, and you got to 9999, 9999 on one calculator, it's going to move to the calculator to the left of it, and it'll show 1 on the calculator to the left, and then a bunch of zeros, right? But the way Intel works, it goes the other way. And it's going to start with, let me hit that right there. There we go. So it's going to go from the middle calculator, if it was going to go from like 9999, 9999 to whatever that is, like 10 million or something, 100 million, it'll go from that, and then the 1 will show up on the calculator to the right of it. And the zeros will be dead in the center again. That is byte order. Big Endian versus Little Endian is how it's typically referred to, as well as Motorola and Intel format. It's something you got to pay attention to when you're watching. If you see an overrun and see which way it goes, it'll typically show you. And don't think that this is something manufacturer dependent. It could be a lot of, for instance, I'll use a good example. Manufacturers like, let's say Hyundai, Kia, they're going to license stuff from Bosch. And if Bosch set it up to where it was Big Endian, but the rest of their car is Little Endian, they're probably just going to accept that. They have to accept that value is going to be Big Endian on their network. So you're not guaranteed, if you see these values just rolling over to the left, that every value on that car is going to roll over to the left at a different arbitration ID if you're looking for different information or different signals. It can be any way possible. And they use these DVC files that you could essentially create in this software here in order to just import that information and program in their devices. Signed versus unsigned. Signed versus unsigned is very, very difficult to kind of comprehend, so to speak. The best way I can explain it is unsigned value is always going to be positive in its raw form. It does not always have to have an end result of a positive value. And what I mean by that is, I'm going to bring this back to 8 here. And we're going to type the factor of 1. And we're going to offset this by negative 128. So, well, I won't jump ahead of myself. We'll start with what it would be. Okay. So if this was a signal that we're showing here based on this grayed out area, and the value is zeros across the board, the answer would be 0, right? We're having a raw value of 0 multiplied by 1 offset by 0. But if I wanted to say, hey, I want this number to be negative 128 to 127, well, here's this offset. So negative 128, right? Now this value, if it was 0, zeros all the way across, we go, okay, we got our raw value of 0 multiplied by a factor of 1. 0 times 1 is 0, minus 128. Now we're sitting at a negative 128 with all zeros here. A good example of that would be if you have a temperature sensor. Most temperature sensors go like what, negative 40 to, I don't know, hot. So and that's in Celsius. They'll use that negative 40 as an offset. So it'll just be an unsigned value to show this on 1 byte. So it goes, okay, we're just going to offset it by 40. So if the value was 0, 0, they have a negative 40 offset. So the value is negative 40 Celsius. Let me go here. Type in signed. Most signed, if you, and this is assuming that it was unsigned. I just didn't change the type. But if you were in signed, you're usually not going to see an offset. And the reason being is that signed value is going to give you the ability to swing both ways. So you don't need an offset in most cases, and it's kind of unnecessary almost. just it would be good to obfuscate the system a little bit, I guess, if you were trying to make sure other people didn't figure out what you were doing, but not necessarily neat. But assigned value looks at the first it looks at the first bit, or it goes basically 0 is going to be 0, right? And it's going to go, if you subtracted 1 from 0, you would go -1. But it's kind of like rolling over again. So if you rolled over from 100 backwards, you would get 99, right? Well, the same thing, the same scenario plays out here. If you rolled over from 0 here, you would just get all ones, which would reference a -1. And then you subtract 1 from that, and you get this 1, 1, 1, 1, 1, 1, 1, 0, which would be -2. If you were looking at an unsigned value, it would look at it as 254. So it's kind of confusing. It's kind of like if you have rollover number cards, you only have the value, like if you had rollover number cards in a decimal form and they were unsigned, you would have 0 through 9. And once you got all the way to 9 and you rolled it over again, you go back to 0, right? Well, on a signed scale, you would have -5 to 4. So once you got to 4 and you rolled it over again, you go to -5, and then you go 4, -4, -3, -2, -1, 0. That's kind of how I got it. I don't know if it helps. It's very confusing. There's a lot of calculators out there for converting that stuff, and I'll add one in the comment section. I'll have it pulled up. And if you have any questions or any more questions, feel free to ask. Also, I'm going to bring up one more thing too. Link has a pretty decent CAN setup template to show you the values, and we're going to add a frame, add a parameter. We're just going to pick something. All right, cool. So it is a start position is 0. All right, so you see the start position, and the width, we'll type 8. Notice that I put in a start position of 0 and a width of 8, and it starts at how they calculated it 7 bits out. But if we go back to this screen here, you can see our start bit is 0. So bit position, 0. Let's go a length of 1 to explain it. So do you see how we're referencing the start positions correctly, but we're numerically incrementing the value to understand where it's at? That's one thing that you want to pay attention to understand in the aspects of setting up a CAN device and CAN network, making sure the start position is actually referencing the start position you think it is, because a lot of times it can be very confusing. If they use a conventional measure, this graph here does a great job. This software here does a great job at kind of helping you get in the ballpark. And if you were looking at this information on a screen at a line level, just watching it like a hex, you would cut 1 and put 1 to the right of 2, or 1 to the right of 0, and then 2 to the right of 1. So this would just be in a very linear fashion instead of rolling over like you're hitting the inner sign. But I hope this helps. Hopefully somebody gets something out of this, and hopefully it wasn't just me rambling a lot. And appreciate your time.